I think I missed.
Okay, so
81.
we were talking about gravitational potential. Okay, so kind of revisiting Kepler here. We have Mercury orbiting the sun.
Ready for that test.
So we've already discussed that the orbits are elliptical. There's two foci in an elliptical orbit. And as I was saying, I forget though, the perihelion is either the furthest away from the focal point or the closest here. Anyway, it's one of those extrema in orbit. And so then we're saying, let's see, we're at the perihelion, the radius there is going to be 4.6 times 10 to the 7 kilometers, and the orbital speed is 59 kilometers per second. Okay, I'm going to guess the perihelion's closer because what we're going to solve for is going to be a slower velocity. So what is Mercury's orbital speed when its distance from the sun is 5.8 times 10 to the 7th kilometers? And very clearly, the radius is getting larger, so I'm going to guess the perihelion is that closer extrema. Okay, so we're using the work energy theorem. So something to think about when you're actually using AI as a tool. When you're solving problems, also don't just accept anything that AI gives you. Make sure you use a prompt that makes the AI use the current theory that we're using. So, and I'll show that in a little bit. Like you might have to specifically say within the work kinetic energy or the work mechanical energy theorem, and then you give it what you're looking for. Because sometimes it will also spit out a solution that doesn't have anything to do with the theory that we're currently studying. So you have to learn how to prompt it to do those things. Because again, if I get a solution that has, like if you're doing a work energy problem and I get a solution that has nothing to do with work energy, I'm going to put comments on there. So make sure you're using it appropriately as a tool. Okay, so for this one, are there any non-conservative forces?
No.
No, the only force at play is gravity. So that means all of our work is going to be conservative, which means we can start with and then I'm going to change this look like that. I just made that change. You could leave it as initial if you wanted to. I changed the I to a P to let me know that the starting point is the perihelion. Okay, so now let's start putting in our equations for these. What is the equation for kinetic energy? If you don't remember this, I would suggest never taking the MCAT.
Okay.
You're going to get like a 200.
1/2 MB squared.
Yep, 1/2 MB squared. Now, what about the potential energy in this instant? Nope. See, we're talking about two orbiting bodies here. MGR is not really going to have a relevance at this. It's not exactly appropriate for this situation. Yeah. So if you remember that, and then that potential energy is going to be a negative. Okay. So then we look through. Okay, so what can we start? Let's start eliminating some things that we can get rid of. What can we get rid of? Yeah, so that's going to be the mass of Mercury. That's going to be the same in everything, so it can go. Now I'm going to go ahead and switch the sides of the equations because we're looking for that to be final. And I have a compulsion to always have my the thing I'm solving for on the left. It's not him. Okay. So then let's get rid of the 1/2. Two. Okay. Now go ahead and say and at this point. Yes, actually, sorry. So at this point, you've solved for the variable. So now this is a place you can go ahead and start plugging the numbers. I'm sure there's a few other simplifications you could do, but if you do them, great, not super necessary. You've solved for the variable you're trying to find. Now there's one more simplification you can use, but so we don't have to write that number a bunch of times. Let's do it. Because when we go into our the appendices of our textbook, G and then the mass of the sun. Okay. And so then we have our two radii from the problem above. And that's a really long thing I'm going to let you write up on your own.
Until the 30th. I didn't know
Yeah.
how much the sun weighs.
Masses and yeah, 10 to the 30th.
How do they know? How do they know the mass of the sun? Do they weigh it? Didn't think so.
No, it's usually by observing gravitational motion. So you look at the motion of the planet. It's the way they discover some of the outer planets. You know, they look at the orbits of the planets. And they say, okay, well, if this planet was the outermost planet, it should move in this kind of orbit, but it's not. that means that there's a gravitational force outside of it that's also acting on it. So there should be another planet there. You can calculate its mass, about where it should be. That's how they found Neptune. You can also, for example, you can watch through a telescope, you can watch Venus orbit the sun, Mercury orbit the sun, Mars orbit the sun. And through all of that motion, you can start to figure out the various masses in the solar system. So again, even though all the planets orbiting the sun does cause the sun to wobble a little bit, it's so massive, you're never actually going to observe that motion. It's a tiny, tiny motion. Okay, so I'm gonna let you plug those numbers in and work with your calculator. But you're gonna get final velocity. In the 14 meters per second. Or 47.8 kilometers per second.
I use kilometers for the half distances, and I need to change my G into kilometers.
In all fairness, I would change everything else to meters, because if you look at the units on that G and
That's
the number, you stand a much larger chance of making an error trying to change the constant.
So change everything.
Yeah, I would make everything match your constants. It's just a safer way to do your calculations. Okay, so we've been talking about work that's done by a constant force. Now we can discuss work done by variable forces. So what? Done force. Minutes. Let's say we have some varying force that is moving across the distance. So we know that we're dealing with the change in work is going to be force delta x. The way we can start looking at that. You're going to have all these little rectangles. Each one of these is a delta x. They top out at a maximum force. And so then, of course, work can be viewed in two different ways, because eventually what we want to get is we want to get the area under the curve, which means that these are going to get rectangles are going to get smaller and smaller and smaller. So you just end up covering the entire area under the curve. And that's going to be your work based off your work based off this changing force. So like we've been talking about, your work is either going to be that, or as we mentioned this the other day, what if we took this and we said, I equals 1 to infinity. This is, of course, going to give us you're not going to have to solve the integral, but still, that's the basic idea. A good example of a variable force. So you've all played with these before. Can you name a very simple device that when you mess with it, the force you have to apply changes based off how you manipulate it? It's very close.
Spring.
Say again?
A spring.
A spring. Think about it. You stretch or compress a spring, you either have to press harder and harder and harder, or you have to pull harder and harder. Because at the beginning, you're not really maxing out the spring constant. Yep. So that's Hooke's law. Okay, so kx, ky, however you want to look at it. A lot of textbooks will measure this up and down as x. If you want to keep that as y, that's also fine. But your force in this case is going to be k delta L. And so k is, of course, your spring constant. You can see that this force varies based off the length of the spring, where it's either been compressed to or stretched to. And so this is known as Hooke's law. Hooke was a very interesting scientist. There's kind of a consensus now he wasn't a scientist at all. I'm sure, as you guys are surprised to find out, in 1600s England was a very hierarchical society. You could be a complete degenerate, but it's like, well, I was born to a highborn noble father, so I'm better than you.
Good accent.
Very much how that society went. It's now commonly believed. So there was this thing called the Royal Society. Isaac Newton was a part of it. Hooke was one of the older members of it, so he was the elite of the elite, and so it's now more believed that a younger scientist discovered this law, and Hooke basically said, well, you're my subordinate, so I'm taking it. So, who knows? That's kind of like when Leibniz and Newton were working on calculus at the same time. The version we use is actually Leibniz's formulation. So in Germany in the 1600s, Isaac Newton was doing it due to analytical geometry in the 1600s, and Leibniz published his calculus first, and Isaac Newton tried to sue him for plagiarism. I try to imagine this, the arrogance of the man saying, well, you copied off of me. It's like, first off, you're in England, he's in Germany, this is the 1600s, there's not exactly the frickin' internet. And also, Newton hadn't even published his calculus yet. Somehow he got a look at my manuscript, copied it down, went back to Germany, and then reformulated it and then published it. Like, really? You think that's what happened? Okay.
I'm gonna lie, your accent's pretty good.
No.
You should do that to like the
I pay attention so much better.
I know we're supposed to be accepting of all cultures, however, my advisor in grad school was British, and
beef.
I'm not real fond of that one.
I'd pay attention so much better.
Do what?
I'd pay attention so much better if you used your accent.
Yeah.
Your accent is so good, you made fun of him so much.
Well, I did.
He knows it's true.
He's got practice.
So it was an interesting time. No, that I could tell you stories about him, but I think some of them would get me fired.
Oh,
And he was your advisor?
Yeah,
Tell the stories. Tell one of the stories that wouldn't get you fired.
so yeah, you kind of get the idea of how that Royal Society in England went, and why this guy Hooke was like, yeah, it's mine, I'm taking it. He was like an old codger by that point. But because of that, now all physics textbooks know this as Hooke's law. Okay, so Let's say you have a handful of bolts weighing 16 newtons placed in a pan on a spring scale. The spring has a spring constant, which is going to be your K, of 5 newtons per centimeter. How far does the string stretch? So let's spring stretch. I do that. Yeah. So let's draw a diagram. So I don't care if you do your diagrams, zigzags. Let's say there's a little pan there. I don't care if you do that. You kind of do your best at making a little spring. Now, the whole point to this is, so we're going to say that's positive Y, and we say we put this mass on the pan of the spring scale. So initially, you could call that Y or X based off how, if you want to do everything in X, that's fine. So there's the 0 position. Every spring has a 0 position. And then you're either going to compress the spring or you're going to stretch the spring away from that 0 position. 2, so we're trying to figure out what that new Y position is. And so then, of course, we have a force of 16 newtons causing the stretching of the spring. Okay, so now keep in mind, stretching is usually seen as a positive distance and compression is usually seen as a negative distance. So with a spring, you can get positive or negative forces based off if you compress or stretch it. But all of them are something called restorative forces. Why do you think they're called restorative forces? Yeah, so no matter what you do to the spring, it's trying to restore itself to the 0 position. So let's start with, I'm going to do this in Y, you can do it in X. Let's start with Hooke's law. Okay. And you could do delta Y if you needed to, but one of those is going to be 0. And so what we end up with, yeah, so you see I set positive Y as the upward direction.
Oh, yeah.
So a lot of time Hooke's law is not that bad to solve. Now we're gonna get an addition to our work mechanical energy theorem. And so the work done by a spring, which is also going to feed into so kinetic energy is what it is, 1/2 mv squared. So this new work equation is also going to feed into what new kind of energy do you think? So your mechanical work energy theorem is your work non-conservative equals what?
The negative K,
Not negative K.
wait, the work energy there?
Yeah.
Oh, that's the 1/2.
That's what kinetic energy is. Let's just make it general. The work kinetic energy, not kinetic, because the work kinetic energy theorem is just delta K. What's the work mechanical energy? Yeah,
Equals
and what are the energies involved?
Kinetic and potential.
kinetic and potential. So up to now, we've had delta K plus delta U. And the delta U we've been working with is gravitational delta U. What do you think this is gonna be? Like gravitational.
No,
Is it like, because it's a restorative?
So it's not gonna be a kinetic energy, it's gonna be a what?
potential.
Potential. So we're edging towards spring potential.
Like,
Okay, so. Let's, because we start with Hooke's law. How do we get to negative 1/2 kx squared? So we start with the fact that we're gonna start with our basic work dot product. And we know that the spring force is negative kx. Okay, so we're gonna say that our F dot delta R is gonna be the spring force delta R cosine of theta. Now, based on the way your spring moves and the direction of the force, the theta is gonna be what? So theta is going to be 0 between the force and the direction of motion. That means cosine of theta is going to go to 1. You're going to get spring force delta R. Now, we're going to have to change this to
Wait, what is that little thing?
the what?
The little thing.
That's a differential.
Differential.
It's a derivative if you have like let's say you have a function with x in it. If you have a d by d, so the derivative working on the function looks like that. The d by itself is just a differential. And so then we change this to be we're going to be working in dx, and that's going to give us negative kx dx. And so then, of course, you get the work.
I gotta go.
K is a constant, we can pull it up front. And so once again, we're using the power rule for integration. Of course, we don't need the integration constant because we're using a definite integral. Definite integrals are the ones with limits on the integral. So based on that, the work is going to be your negative k. And so based off the power rule, what does x dx become from the integral? So yeah, so your n is a 1, your exponent's a 1. And so 1 over n plus 1, 1/2, and x, and then the exponent n plus 1 is squared. We're going to evaluate initial to final. We know the difference. 1/2 final squared minus 1/2. It's initial squared. So the work is going to be negative k. Let's see. Actually, we're going to bring k on the inside. So negative 1/2 k squared plus 1/2 k. It's initial squared. Now, you see that that feeds into our generalized equation for the work done by a spring, the 1/2 kx squared, the negative 1/2 kx squared. And so how does work compare to change of potential? We're gonna call this the work of the spring. How does work compare to the? So yeah, so we're talking about it here. So we're now feeding into the potential energy of the spring. And how does work compare to potential energy? Remember, your delta U is always going to be negative W. So if we go back up, you take this, and we multiply it by -1, we get the potential energy of the spring, so the delta U. And in particular, this is called an elastic potential. So any object that you deform, and then energy, it picks up energy in its deformation, that's going to be elastic potential. For example, a bow and arrow exhibits this. When you hold the string on the bow, you deform the bow. If you're holding the string, you have elastic potential in the bow. When you deform a spring, you stretch it or compress it, you have elastic potential. Elastic potential comes from a material that's trying to restore itself to its original shape. So this is going to give you that's going to be your change in elastic potential. And so now, let's see. Yeah, so. Okay, so we will finish up this chapter on Wednesday, and then we're going to start moving on to the momentum. I really wish we could get into a fun topic, because you know how you get velocity from changing position. You get acceleration from changing velocity. What do we get from changing acceleration?
It was so up and down.
It's a fun physics thing, so jerk, change your acceleration.
You said, probably not here. They wanna throw in.